feel like I had a question. Like, I know has he given any guidance or information about that homework question about the ratio test and the root test? The one on the current homework about like how if the ratio test works, then the root test also has to work or something like that. Okay. Also, I feel like the other day I was helping you with the problem, but I was helping you with the wrong test. Because it was the problem where it was supposed to show the integral test showed convergence, and it was the root test shows divergence. Right, I was doing the ratio. Now, the examples we came up with will still work. So for example, if you do like the integral, if you do 1 over x squared or 1 over n squared, that sequence has, if you do the integral for the, so I'll just point out. I was doing this the other day. So I will mention here, Co-21C. Today is April 21st. I will just point out that, for example, if you look at this series, n equals 1 to infinity of 1 over n squared, obviously convergent. We know it's convergent because it's a p series. Now, really, the way we actually showed that p series were convergent for p greater than 1 was by doing the integral test. So this converges, and we can show that the integral from 1 to infinity, we can say this converges because the integral from 1 to infinity of 1 over x squared dx converges. I'll point out that this converges to 1. But if you're doing this homework problem, you should definitely show that work, right? I'm just going to say it right now, but I would say that converges to 1. And then I will also point out that the root test here, which is what we were supposed to be talking about, the root test is inconclusive. And again, I think you should show the work for this, but I will tell you that the limit as n goes to infinity of the nth root of the absolute value of your sequence, that limit is going to be 1. Now, I would drop the absolute values because we don't need them, and I would rewrite this as the limit as n goes to infinity of 1 over n squared to the 1 over n power, or maybe even one more simplification as 1 over n to the 2 over n, and that limit is equal to 1. I think, well, actually, no, I believe somewhere, someone has said that if you have n to the 1 over n, the limit of that as n goes to infinity is equal to 1, and you can use that, or you could do some L'Hopital's rule stuff here using an e to the natural log kind of deal. So, just wanted to point that out. I was leading you astray the other day. I didn't mean to be. Yeah. Let's go ahead and continue. So I see he posted a practice midterm. You should definitely look at it. I would say, as with, I mean, I don't know. I think this test looked reasonable in length. Like this seems like a not totally out there possible actual exam. I would say, like I would usually say, if you're given a practice test and it's actually a practice test, not like a review, you should give yourself 50 minutes someday, maybe next week, maybe this weekend, take the test, and then look at the solutions afterwards. But really, like, give yourself a testing situation where you just have 50 minutes to work on it. If you really want, you can take it on your own, and then I will grade it for you if you would like. I'm happy to grade a practice exam. It doesn't take me much time to do that. To give you some actual, I mean, obviously my grading might not be the same as your teacher's grading, but I imagine it would be similar enough that you would have a good idea of, okay, I need to work on this or work on that. But yeah, I would say definitely take a look at that practice exam. It is worth your while. All right, let's go ahead, and I was going to continue talking about power series. The power series. It's really just say ways of writing functions as infinite sums. So last time we started off with kind of the most common example you ever see in this, which is that 1 over 1 minus x is equal to 1 plus x squared plus x cubed, and so on and so on and so on. And it's the sum from n equals 0 to infinity of x to the n. And I will point out, this is only true on the interval of convergence. So this is only true for x between -1 and 1, or usually just write the absolute value of x is less than 1. Which is not surprising because it really just looks like something that's geometric where the ratio is x. And so when that's the case, for the series to converge, the ratio has to be between -1 and 1. Yeah, so let's look at some more examples. So I will say the first kind of rule of thumb for dealing with power series is if you can make it look like that, then you should. Here's what I mean by this. Let's say I want to find the power series for, say I want to find the power series for x over 1 minus x cubed. Well, that looks a lot like what a geometric series adds up to. This looks a lot like a first term over 1 minus a ratio. In fact, I'm actually going to do it that way. I'm going to say, great, my first term is x, my ratio is x cubed. If I start writing this out, it looks like x plus x cubed times x is x to the 4th plus x to the 7th plus x to the 10th, and so on and so on and so on. I'll talk about another way you can get there as well. But if it's really kind of a very direct kind of, we can see how this is working really easily. I just like to do it like that. Now, if I actually want to write this as a formula, it's going to be the sum. I'm usually going to start at 0. And then I know I want to start with x to the first. So I need an x, and then I need to multiply by an x to the third. So I would maybe write this as x to the first times x to the third to the n. So that every time n increases by 1, I'm going to multiply by another multiple of x to the third. And then we could simplify this and write it as the sum from n equals 0 to infinity of x to the 3n plus 1. Just like with our previous example, this converges if your ratio, which is x cubed, is between -1 and 1, which is the same result, that x is just between -1 and 1. Now I'll say this is not always how I like to see it. Here I'm going to back this up and kind of view this another way. So here's what I really look at. When I see this, I'm really trying to make x over 1 minus x cubed. I would love for this to look like 1 over 1 minus some stuff. We want this to look like 1 over 1 minus some stuff. That's what I would really like to have. So the way I'm going to do that is by factoring out whatever's on top. I'm going to say, great, this is equal to x times 1 over 1 minus the stuff. And the stuff is x cubed. And then I know that 1 over 1 minus my ratio, this part here is just going to be, that's where you have your 1 plus x cubed plus x to the cubed squared plus x cubed cubed, and so on and so on and so on. Some people see it better that way. I don't know. Like maybe you like it better the first way, maybe I go the second way. But either way, I'm trying to write it like this. So then I say, oh, 1 over 1 minus my ratio, that's just going to be the sum of 1 plus the next term times ratio plus the next thing times ratio, and so on and so on. I do it this way because I feel like it's easier to see this pattern. And then I can say, well, that's just going to be x times the sum from n equals 0 to infinity of x to the third to the n. And then that x that's outside can come inside the summation. And so that's going to be the sum, just like we had before, of n equals 0 to infinity of x times x to the 3n, which is just x to the 3n plus 1. So a lot of the time, finding a power series for a function is manipulating your function to make it look like 1 over 1 minus a ratio. That is, usually if we can do that, we're going to do that. Let's look at another example. So we're going to say that I want to start with the series for f of x equal to 1 over 1 plus x. And then I'm going to integrate it and get a series for g of x equal to the natural log of 1 plus x. Because the integral of 1 over 1 plus x is the natural log of 1 plus x. Kind of neat. All right, so 1 over 1 plus x, I really want that to be 1 over 1 minus my ratio. And so I'm just going to make it that. I'm going to rewrite f of x equal to 1 over 1 plus x as 1 over 1 minus x. I'll say this many times. We're really trying to get to making it look like 1 over 1 minus a thing. If we can get to there, we're kind of golden. And really the whole idea of this is that we're kind of shortcutting the process of doing the whole Taylor polynomial expansion. Right? There's this whole other thing we're going to talk about where you take a bunch of derivatives and plug in some stuff and then find the formula that way. And that is usually taking longer than we want to. We'd rather not do that unless we really have to. So here, 1 over 1 minus my ratio is just going to be my first term plus my first term times my ratio plus my next term times my ratio, and so on and so on and so on. Which I would probably drop the parentheses and just write it as 1 minus x plus x squared minus x cubed plus x to the 4th, et cetera, et cetera, et cetera. And then we can write that as the sum. Now, I will point out, you could write it as the sum of just negative x to the n. But I'm going to tell you, it is usually in your interest to try to isolate the x part without any other coefficients attached to it. Because if we're going to try and anti-differentiate or differentiate this thing, which we are going to do some of the time, it's easier to anti-differentiate x to the n versus negative x quantity to the n. I don't want to do a u sub. So I would rather write this as the sum from n equals 0 to infinity of negative 1 to the n times x to the n. That's usually going to be a little bit better for me. And here's something that's really lovely. If you have a function equal to a power series, the antiderivative of that function is equal to the antiderivative of that power series. So I can say that the antiderivative of f of x, which is equal to the antiderivative of 1 over 1 plus x, which is equal to the natural log of 1 plus x. I'm going to ignore the absolute values here, even though normally I would write them down. That's going to equal the antiderivative of this whole thing. 1 minus x plus x squared minus x cubed plus x to the 4th minus x to the 5th, etc. Now, we can anti-differentiate this term by term, but we really don't have to. But let me show you what we get. So if we anti-differentiate term by term, we get x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5, so on. But I really just write that in a formula. So I'm going to, and so instead of like trying to come up with a formula here, what you can actually do, I forgot one thing, sorry. All this plus c, there is a plus c over there. Plus c is coming. Instead of doing all this, I can just look at my summation for this series and say, well, if I anti-differentiate x to the n, I get x to the n plus 1 over n plus 1. And that is the formula. This is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. Does that check out? Yeah, that checks out. If I plug in n equals 0, I get 1 times x to the 1 over 1. Yep, that's my first term. If I plug in n equals 2, I get, maybe it doesn't quite, I might be off by am I off by a negative here? Oh, no, sorry, I went to 2, I should have went 1. Plug in n equals 1, I get negative 1 times x squared over 2. There we go, and so on. Keeps going. Plus c. Here's what I'll say about the plus c. It's not always going to be 0, but it is often going to be 0. The way we find what the plus c is by plugging in the center of, I forgot to say something important. It's not like I totally forgot, but I will point out that this thing converges. Well, actually, let's just find where it converges. So I will say here, for this geometric series, the interval of convergence is x being between negative 1 and 1. Or whatever your ratio is between the table. Or I guess I could even write it as the interval from negative 1 to 1. So now let's find the interval of convergence by using the ratio test. And this is something I guess we haven't talked about in this class. You might have already talked about in your actual class. When you're trying to find the interval of convergence for a geometric series, for any power series, we typically use the ratio test. So what we're going to say here is that to define the interval of convergence, we're going to use the ratio test. You could also technically use the root test if it was a nice thing all raised to the nth power, but you're almost always going to be using the ratio test. So let's see, if I look at this thing here, it's going to be the limit n goes to infinity of my n plus 1 term. So -1 to the n plus 1 times x to the n plus 2 over n plus 2 times the reciprocal of my n term, which is n plus 1 over x to the n plus 1 times -1 to the n. And we really do need the absolute values now. Okay, we're going to simplify. I will point out -1 to the n plus 1 over -1 to the n. That's just going to be -1, which doesn't really matter, especially if it's in the absolute value. So we're just going to kind of ignore that. And we're going to get the limit as n goes to infinity of, I'm going to have n plus 1 over n plus 2. And then I'm going to have x to the n plus 2 over x to the n plus 1. But that just reduces to x. So what I really have is the limit as n goes to infinity of the absolute value of n plus 1 over n plus 2 times x. But that's just equal to 1 times x in absolute value. So why have we done this? What is this telling us? Well, when you use the ratio test says the series converges if this limit is what? Good question. If the limit was 5, would we say that the series converged or diverged? So we would say it diverged. And if the limit was, say, like 1/3, then we would say that the series converged because that limit is less than 1. So what we're saying here is that the limit here is the absolute value of x. And then we're going to say, well, for this series to converge, that absolute value of x has to be less than 1. So that's the whole idea when you're trying to find the interval of convergence and also the radius of convergence for a series. You're taking the limit of the power series using the ratio test and eventually getting some condition about the values that x is allowed to be. So here we get x between 1 and -1. Now, we're not quite done, and I can't imagine your professor is going to let you finish with this. If this limit were greater than 1, we would get divergence. If this limit were equal to 1, what happens when the ratio test is equal to 1? Right. That means when x is either 1 or -1, we actually don't know if the series converges or diverges. So we're going to check. So usually when you're finding an interval of convergence, we check the endpoints. So if x is equal to 1, we're going to have the sum from n equals 0 to infinity of -1 to the n times 1 to the n plus 1 over n plus 1, which is just the sum from n equals 0 to infinity of -1 to the n over n plus 1. That's an alternating series that definitely meets all of the necessary conditions to converge. This converges by the alternating series test. Our sequence definitely is, our non-alternating sequence is positive. The limit of it is definitely 0, and it is for sure decreasing. I guess I can write that. So here's what I'll say. When you're testing endpoints, you usually don't have to like show all the work. You just have to kind of state the relevant theorem. So, but I will say the work here would be to say, oh yeah, the non-negative terms or the non-alternating part, 1 over n plus 1, certainly positive. The limit of that certainly equal to 0, and definitely it's decreasing. The next term is smaller than the previous term. 1 over n plus 1 plus 1 is definitely smaller than 1 over n plus 1. But I don't really think you need to write any of that down unless your teacher says you do. Okay, that was one of the endpoints. Let's check the other one. So if we check x equal to -1, the story is going to be different. So when we do that, we're going to have the sum from n equals 0 to infinity of -1 to the n times -1 to the n plus 1 over n plus 1. All right, -1 to the n times -1 to the n plus 1. If n is 1, I get -1 times +1, which is -1. If n is 2, I get +1 times -1, which is -1. If n is 3, I get -1 times +1. It seems like it's always going to be -1, and it is. If we rewrite this as the sum from n equals 0 to infinity, if we add those powers, you get -1 to the 2n plus 1. And -1 to the 2n plus 1, 2n plus 1 is always going to be an odd number. So -1 to that power is always going to be -1. So we can write this as the sum from n equals 0 to infinity of -1 over n plus 1. Or if you like, I kind of like to pull out the -1 in front and write it as -1 times the sum from n equals 0 to infinity of 1 over n plus 1. We know that this is a divergent series. You can say it diverges by, I don't know, limit comparison with 1 over n. Okay, so here's what we get to say. This series, that's the power series for the natural log of 1 plus x, which is equal to the sum from n equals 0 to infinity of -1 to the n times x to the n plus 1 for n plus 1, converges, meaning we get to say it's true, these are equal to each other, if x is less than or equal to +1 and strictly greater than -1. Or in other words, the interval of convergence is -1 to 1. Is there anything else I want to say here? So it is not a coincidence that the intervals are practically the same. The original series, 1 over 1 plus x, which I know is way up here, sorry, give me 1 second. The original series, 1 over 1 plus x, the interval for convergence was between -1 and 1. And here, it's almost the same, we're just including the 1. The length of the interval is essentially still the same. And this is actually always true whenever you differentiate or anti-differentiate a function. Its interval stays the same, except you might have to include or exclude an endpoint that you didn't have to before. Let me say a couple things before I write that down, though. So I just want to point out that we could use this series if we wanted to approximate the natural log of a number between -1 and 1. Well, I should say the natural log of a number between where x is between -1 and 1. So for example, I can say that the natural log of 3/2, which is really the natural log of 1 plus 1/2. If I wanted to use, say, like the first 3 terms, it would be approximately equal to, I'm just going to plug in n equal to, or sorry, 1/2 from x. I'm going to look back at my previous way of writing this just to make it a little bit easier. So I'm just going to plug in x equal to 1/2 and get approximately, well, let's see, 1/2 minus 1/2 squared over 2 plus 1/2 cubed over 3. And if I simplify this, it's equal to 5/12, which is approximately 0.4166. Well, not approximately 6 forever. Let's just go with the 7 bit. If you use a calculator, the natural log of 3/2 is approximately 0.405. It's a pretty good approximation of the natural log of 3/2 without doing too much terrible work. Here's the point I want to make, though. I don't really care so much that this is a good approximation. We can find natural log of 3/2 many other ways. But if you pick a number for x that is outside of the interval of convergence, you don't get that these are matching up. What you get is that, say, for example, if I want to say the natural log of 5, which is the natural log of 1 plus 4, it is not going to be approximately equal to, let's see, 4 minus 4 squared over 2 plus 4 cubed over 3. The natural log of 5 is approximately 1.61. Whereas this number over here is, let's see, that's 416 over 2 is 8 plus 64 over 3. That's about 17.33. Those are very, very different from each other. So the whole point to see here, the thing to take away from this is just that we can say that this function is equal to this power series only for the values of x in the interval of convergence. So we get to say that the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3, et cetera, et cetera, et cetera, as long as x is between -1 and 1. Cool. The thing that I kind of skipped over, but I definitely should roll back around to, is what the whole plus c part. So just to kind of back it up a little bit, I had said before that the natural log of 1 plus x was equal to the sum from n equals 0 to infinity of -1 to the n times x to the n plus 1 over n plus 1. And then I said there was a plus c out here. The way you find the value of c is you plug in x equal to the center of the interval of convergence. So if our interval of convergence is -1 to 1, the center of that is 0. So we're going to plug in x equal to 0 and see what you get. So on the left-hand side, I get the natural log of 1 plus 0, which is the natural log of 1, which is 0. On the right-hand side, if I plug in 0 for x, well, look what I'm getting. I'm getting 0 to the 1 over 1 minus 0 squared over 2 plus 0 cubed over 3 minus 0 to the 4th over 4. And then finally, there's a plus c at the end. So here's what really happens. Whenever you plug in the center, all of the terms in the summation are just 0, because the center is the value that makes everything equal to 0. So when we're plugging in that center, all these are going away, and then you just end up getting that c is equal to whatever the left-hand side is equal to. And most of the time, not all the time, most of the time that's going to be 0. So here's the thing to take away from this example, or one thing to take away. There's this integration / differentiation theorem. Basically says you can integrate or differentiate any power series, and the new power series will have the same radius and interval of convergence, with the endpoints being exceptions. So if we integrate or differentiate a series that converges for x between, I feel like the more official way to say it is x between a plus r and a minus r. So the center is a and the radius is r. The new series also converges for the same interval, x between a minus r and a plus r. But we have to test the endpoints. And literally anything can happen to the endpoints. You could have a series that didn't converge to the endpoints, and its derivative or antiderivative will converge. It can converge at one or at both or at neither. And it doesn't matter if your original series converged or didn't converge to the endpoints as far as the new series is concerned. So the rule of thumb here is really always test the endpoints. Let's look at another example. Yeah, we got time. Here's another kind of classic example. Let's say we want to find the power series for f of x equal to the arc tangent of x. Ooh, that's really blurry. So you could totally do this if you knew the Taylor's formula, which you might have already seen. But even if you knew Taylor's formula and you wanted to use it, I would say you shouldn't, because that is the harder way to do this. The easier way to do this is to say, well, I don't know what arctangent power series is, but I definitely know that if I take the derivative of arctangent, the derivative of the arctangent of x is 1 over 1 plus x squared. So then I can write this as, oh, that looks like 1 over 1 minus something. I just have to rewrite it. It looks like 1 over 1 minus negative x squared. And then we can say that's going to be, well, my first term is 1. My ratio is negative x squared. That's looking a lot like the sum from n equals 0 to infinity of negative x squared to the nth power. Which again, I think it is in your interest to rewrite as the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n. Excuse me. I will also point out, so it's always good to say, right, this series, the original, or sorry, the derivative here, this thing here, this definitely converges for my ratio, negative x squared being strictly between 1 and negative 1, or the absolute value of negative x squared being less than 1. And if your thing looks like a geometric thing, right, where it's 1 over 1 minus some stuff, you don't have to test the endpoints. Geometric series specifically never converge at the endpoint. So here we can say, great, calm down. So that just means that x is between negative 1 and 1. Right, x can't be bigger than or equal to 1 or less than or equal to negative 1, because then it'll just be too big or too small. Okay, so we expect that our new series is also going to converge on the same interval and maybe at one or both of the endpoints. So I took the derivative of arctangent to get this series. To find the actual series for arctangent, I'm going to do the antiderivative. So as the derivative of the arctangent of x is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n, I'm going to anti-differentiate both sides and say that the arctangent of x is equal to the integral of this. And normally I would just kind of do the integral, but I want to point out your teacher might say something about this. They might say something about how if you take the integral of the sum, you can pass the integral through the sum. So you can actually write this as the sum from n equals 0 to infinity of, I would even pass it through the negative 1 to the n, and it's going to be the sum of negative 1 to the n of the integral of x to the 2n dx. That is a true thing we can do. And we know how to integrate x to a power. You're just going to get the sum from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1, 2n plus 1. And that is your arctangent series. Now, what about, so here's the thing. Last time we did the ratio test to see what the interval of convergence was. This time we don't have to do that because of the theorem we just said. The interval of convergence is the same. It's also going to be negative 1 to 1. We just have to test the end. So let's test x equal to negative 1 first. So if x equals negative 1, we have to be really extra super careful. Like it can be really easy to convince yourself of something that's wrong when it's really right, or right when it's really wrong. So if I plug in negative 1, I get the sum from n equals 0 to infinity of negative 1 to the n times negative 1 to the 2n plus 1 over 2n plus 1. And the question that this often boils down to is this thing alternating or not? Well, you can check a few terms if you really wanted to. What I would probably say is, well, -1 to the 2n plus 1 is always going to be -1. Because -1 to the 2n plus 1, 2n plus 1 is always odd. But then the other -1 to the n is going to alternate back and forth between negative and positive. So it looks like this is alternating. We could also just combine them together and say this is the net sum from n equals 0 to infinity. When you add those powers, n plus 2n plus 1 is 3n plus 1. And then the question is, does that power go between even and odd? And it does. If n is 0, this is odd. If n is 1, this is even. If n is 2, this is odd, and so on. So this converges by the alternating series test. Because again, right, once we've seen that it is alternating, definitely the 1 over 2n plus 1 meets all the criteria. It is positive, its limit is 0, and it's certainly decreasing. Let's check x equal to +1. And I think we're also in the convergence here, because if x equals +1, we get the sum from n equals 0 to infinity of -1 to the n times 1 to the 2n plus 1, which is just 1 over 2n plus 1. And in a similar fashion, this series, which is -1 to the n over 2n plus 1, that's an alternating series. It's the same alternating series. This also converges by the alternating series test. So for this new series, arctangent equal to this, we get the excuse me, interval of convergence is -1 to 1. Let me ask you two, I think, fairly straightforward questions about this interval. For this interval from -1 to 1, what's the center? Right. It's really literally the number in the middle of the interval. And what's the radius? Right. Right. I'm not asking trick questions here. The radius is just how far it is from the center to either endpoint. Or if you prefer, the total length, the diameter, divided by 2. Because the length from -1 to 1 is 2, and 2 divided by 2 is 1. Either way you want to see it, it's totally fine. But that's how I would generally think about how you're actually finding the center of the radius. There's other mathematical ways of finding it. I really think finding the interval and then just seeing it from there is the way. Oh, that's kind of interesting. Here's a cool fact that I'm just reading on this. So interesting fact. You don't need to write this down. I just think it's neat. So if you plug in 1 for x into this series, which is in the interval of convergence, so we can. So if x equals 1, we get arctangent of 1 on the left. On the right, we get, let's see. Well, I'm just like here. Oh, no, sorry. I guess I just have to plug in terms. So if n equals 1, I get, sorry, if n equals 0, I get 1 to any power is 1 over 1. So I get 1. If n equals 1, I get x cubed over 3, but it's negative. I get -1/3. And then the next term is going to be +1/5, -1/7, and so on and so on. You might not think this is super neat, but if you remember what arctangent of 1 is, it's kind of cool. What is the arctangent of 1? It's the angle that if we take tangent of the angle, we get 1. Pi over 4. Tangent of 45 degrees is 1, or tangent of pi over 4 is 1. So this actually gives you a really kind of funky, neat way of estimating pi. We can say that pi is equal to 4 times 1 minus 1/3 plus 1/5 minus 1/7, and so on and so on. Do you need to know that? No. But is it neat to see some cool things about math every once in a while? Yes. So yeah, that's kind of cool. Sure. Yeah, we should do both of these. Yes, we got. Yeah. Okay. Yeah. Squeezing a couple more. So Monday we'll talk about Taylor polynomials because we're not quite there yet. But let's look at these. Yeah, we can do these two examples. Oh yeah. Actually, so I guess I should say. I don't know. I'm not gonna do that one yet. Actually, let's skip that one for now. So let's say we wanted to find the interval of convergence for the following series. Sum n equals 1 to infinity of x minus 3 to the n over n to the fourth times 2 to the n plus 3. Oops, can't quite see that. Sorry. One thing I'll point out is that although I spoke about finding the interval convergence the center in a different way, you and me and everyone should all be able to look at a series after some practice and be able to immediately see what the center is. Because the center is the value of x that we can plug in and make all the terms or almost all the terms be equal to 0. So here, the center is what? Right. Because if you plug in 3, 3 minus 3 is 0. And all the terms become 0. So the value of x that makes all, occasionally there's a first term where you don't plug the center into that, and so it's like there's a constant term that you don't get to be 0, but essentially all terms equal to 0. Okay, so now if I want to find the interval of convergence, I'm going to apply the ratio test. So to find the interval of convergence, ratio test. In fact, I will just make a blanket statement here. Whenever someone says find the interval of convergence, if you haven't already done something by like taking a derivative or an antiderivative to get there, and you already know what the interval is, you're going to be applying the ratio test. So we're going to do the limit, n goes to infinity of the n plus 1 terms, so x minus 3 to the n plus 1 over n plus 1 to the fourth times 2 to the n plus 1 plus 3 is n plus 4, and then times the reciprocal of your nth term. So it's going to be n to the fourth times 2 to the n plus 3 over x minus 3 to the n. And you absolutely, pun intended, need the absolute values here. Because you're trying to get a condition on x, and so right, if you just end up saying, like if you did all this and you're just saying like x minus 3 is less than 1, then you would end up essentially saying, well, x could be super duper negative when that's really not true. Why are you so too sensitive? Okay, so simplify. This is why we spent time practicing the ratio test before, also, so that we know how to simplify this sort of thing. We're going to group the like terms together. I think you can be a little bit kind of brief with your work here. I would say, well, x minus 3 to the n plus 1 over x minus 3 to the n, that's just going to be x minus 3. 2 to the n plus 3 over 2 to the n plus 4, the power of the denominator is 1 higher, so I'm going to end up with a 2 to the first in the denominator. And then the n to the fourth over n plus 1 to the fourth, the limit of that's just going to be 1. So if you have powers of n, they almost always end up just kind of canceling each other out, for lack of a better term, when you take the limit, because you're going to have some constant times n to the highest power over essentially the same constant times n to the same highest power. The limit of that kind of thing is always going to be 1. So this is definitely going to go to 1 to end up getting x minus 3 over 2 in absolute value less than 1. Right? Because it has to be less than 1. I will point out, at this moment right here, it is very easy to identify both the center and the ratio. Sorry, the center and the radius, apologies. The center, like we already said, is x equal to 3. The radius is 2. Or whatever you're dividing x by. Or the reciprocal of whatever you're multiplying x by. Let me show you though, because maybe it's not, and it's probably not immediately obvious to you. It is to me because I've done this for literally many, many years. But what we can do is we can just solve for x. Multiply both sides by 2. So you have the absolute value of x minus 3 is less than 2. And then we write this as x minus 3 less than 2 bigger than negative 2. Or adding 3 to every side, x is less than 5 bigger than negative 2 plus 3 is 1. The center of that, certainly 3. The length of that interval is 4, and so half of that length is 2, which is your radius. So our interval of convergence, well, we're not done with the interval of convergence yet. The radius for sure is 2. Sometimes when I think when professors are kind, nice, they only ask for the radius and they don't ask for the interval. I will point out, if you only get asked for the radius of convergence, you don't have to test the endpoints. The radius doesn't change, right? For example, if your interval is from 1 to 5 and you're including 1 and 5 or you're excluding 1 and 5, the length of that interval hasn't actually changed. So the radius is going to be 2 either way. Let's test the endpoints. Let's test. I mean, here's what I would say when you're testing endpoints. If you have an idea of which endpoint is going to make it not be alternating, I would test that one first. So let me ask you both. Can I say the words? If I'm going to plug in either 5 or 1 to my original series, which of those is more likely to make it be alternating? The 1 or the 5? The 1, because when we plug in 1 minus 3 is negative. And the negative number raised to the nth power is going to possibly or more likely bounce back and forth. Whereas the 5 is most likely not. So I'm going to start with the 5. And then I'll tell you why in a minute here. So if I test x equals 5, I'm literally just plugging in 5. I do recommend actually just rewriting your series where you say, oh, I've got 5 minus 3 to the n over n to the 4th times 2 to the n plus 3. And then usually this simplifies in some sort of nice way. This is going to equal the sum. 5 minus 3 is 2. And 2 to the n over 2 to the n plus 3, I can subtract those powers. 2 to the n over 2 to the n plus 3, n minus n plus 3 is going to be 2 to the negative 3. So I'm going to get 2 to the negative 3 over n to the 4th. 2 to the negative 3 is just a constant. I don't care about it. What I care about is the fact that I have 1 over n to the 4th. If I factor out the 2 to the negative 3. And we know that that series is convergent or divergent. Well, it's a P series. P is much larger than 1. This is definitely convergent. Here's why I say test this one first. Because now if we test the other one, x equal to 1, I'm going to have the sum from n equals 1 to infinity of 1 minus 3 to the n over n to the 4th times 2 to the n plus 3. And the problem here is that, oh, not really, the problem so much is this one is alternating, right? This is negative 2 to the n over 2 to the n plus 3 over n to the 4th. But I know that since this one is convergent, I could take the absolute value of this one and show that this is absolutely convergent, which means it's convergent. So if you know that the non-alternating one converges, the alternating one is essentially the same thing, but just alternating is also going to be convergent. On the other hand, if this one had been divergent, then I would actually have to do some work here to see that this was convergent. But I can say that this is going to be the sum of negative 2 to the n over, I'm actually going to simplify this bottom part here, n to the 4th times 2 to the n times 2 to the 3rd. I'm going to bring the 1 over 2 to the 3rd out in front, or 2 to the negative 3 if you prefer. And I will point out that negative 2 to the n over 2 to the n is the same as negative 2 over 2 to the n, which is just negative 1 to the n. Spelled n to the 4th. And this series definitely converges. You can either say it's convergent as an alternating series, right, by the alternating series test, but you can also just say this is absolutely convergent. See above. So our interval of convergence is everything from 1 to 5 inclusive. So our interval of convergence here is bracket 1 to bracket 5. You know what I want to say about that? So, yeah. I'll take one more quick example, just because I feel like I owe you one more example. But let's look at e to the x. So even though it's not a function that looks like 1 over 1 minus something, e to the x is probably the most commonly known Taylor series, Maclaurin series, whatever you want to call it. And it's equal to 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial, and so on and so on and so on. one way you can see this without having done any of the Taylor series or Maclaurin series stuff yet is by taking the derivative. The derivative of e to the x, well, the derivative of 1 is 0, the derivative of x is 1, the derivative of x squared is 2x over 2, the derivative of x cubed is 3x squared over 3 factorial, the derivative of x to the fourth is 4x cubed over 4 factorial. But look, I get the same thing. I get 1 plus 2x over 2 is x. 3x squared over 3 factorial. Well, 3 factorial is really 3 times 2 times 1. 3's cancel, and you're left with a 2 factorial on the bottom. Same deal here. 4 factorial is really 4 times 3 times 2 times 1. The 4's cancel, and I'm left with 3 factorial on the bottom. So that's one way people justify this without having shown any of the other work we talked about later, is that, well, yeah, I took the derivative of this thing and I got the same thing back. And we know there's only one function that really does that. E to the x is the only function really that's its own derivative. So this is the power series for e to the x. Let's talk about the interval of convergence. And I guess I could write it out, right? It's the sum from n equals 0 to infinity of x to the n over n factorial. In case no one said it, I know we're out of time, but I'll just, so this is real quick, I promise. Just in case no one's ever said it, 0 factorial is equal to 1. The way it's kind of like how we define 5 to the 0 equal to 1, because we need it to be same deal here. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2 times 1, and so on and so on. Interval of convergence here, super duper fast. Take the limit as n goes to infinity of the an plus 1 over an term, which is just the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, absolute values. That over that is just x. And n factorial over n plus 1 factorial is just going to give us an n plus 1 in the denominator. And now the thing you have to recognize here is that x is just a real number. X could be 5 or 1,000 or a billion, but x isn't infinity. X can be as large as you want it to be, but once you've picked the value for x, that's finite. And then the limit of a finite number over something that's getting infinitely large is, and no matter what x was, this is always 0, and 0, by the way, is always less than 1. Fun fact. That means that no matter what x was, this is going to converge. So the interval of convergence here is all real numbers, which is really, really lovely. That means that e to the x is equal to this expansion, regardless of what value of x you want to put into it. And I'll just say the last thing, the radius of convergence is infinity. So if your interval is all real numbers, your radius is infinity. Well, so I will say there are other functions, notably sine and cosine, that also have an interval of convergence that is everything. Those are probably the three main ones that we see. Sine, cosine, and e to the x all have an interval of convergence that is all real numbers. All right. Thanks for hanging in there with me. Have a lovely weekend. Monday, we'll talk about Taylor's polynomials, Maclaurin series, all that kind of jazz. And then Wednesday, I guess we'll try to review for your midterm that's going to be on Friday. You're welcome.